Good morning. This is Dr. N. Sri Ramya, Assistant Professor from Civil Engineering Department. Today, our topic is boundary layer thickness in hydraulic engineering. Sessions we have discussed what is boundary layer. Right now we are seeing what is a boundary layer thickness. Right. So boundary layer. The first we see boundary layer. So boundary layer is a very thin layer which is formed near the walls, at the walls. If this is your pipe, due to this solid boundary, we are seeing some frictional resistance at the walls or at the surface or at the boundaries due to the surface roughness. Due to the surface roughness, there is a frictional resistance forces acting at the boundaries, right? Due to this frictional resistance, the flow is getting restricted at the boundaries, right? So we have seen the velocity distributions in a pipe. In a pipe, we have seen a velocity distribution in a vertical direction, in y direction. If this is your x direction and this is your y direction, then when you move in a y direction, if we take a component like a velocity, if you take a component a velocity, right, at the velocity is zero at the boundary. As you are moving upwards away from this boundary, you see some velocity variations. At this point the velocity is completely zero. The velocity is completely zero at the boundaries. At here also, the velocity is zero. Throughout your pipe, the velocity is zero in 3D. I'm talking about here 2D, only y and x direction here. In this direction, when you take this cross section, right, here at the boundaries, you see velocity is zero, right? As you are moving away from the boundary, you see there is increment in the velocity. That is increment in flow. The flow at the boundary is not moving. That's mean that is the velocity is zero, right? As you are moving away from this boundary, you are seeing some variations in velocities in y direction, right? That we are calling as a velocity gradients. This is what a velocity gradient is, right? At boundary, it is zero. As you're moving upwards, the velocity is increasing, right? At velocity is increasing. This is what your velocity is. At center, the velocity is maximum. And at boundaries, the velocity is minimum. Right? Due to this frictional resistance, due to this boundary, we are seeing a thin layer. At this boundary, we are seeing a very thin layer. At solid surface, that's mean that at the wall or at the surface, where the effect of fluid viscosity are significant and causing a velocity gradient. And velocity is also one component, and the surface roughness is also another component, right? These all are making a flow to resist at the boundaries, right? So if the viscosity is high, then the flow moving in a pipe is not that much fast. Therefore, the velocity is minimum. For viscosity is more, which is having a more for the fluids, right? If the fluid is having viscosity is high, then your velocity is low, right? So depending upon your roughness and depending upon your viscosity of the fluid and depending upon the surface roughness, there we are seeing frictional resistance which is opposing the flow and which making to form a boundary layer, that is a thin layer which is occurring at the boundaries, right? And here the velocity is 0 at the boundary because of no slip condition. No slip condition means there is frictional resistance is active. At there the frictional resistance is acting, right? The frictional resistance is acting at the wall, right? To the free stream value away from the surface, right? At the center, the velocity is maximum, right? So till this point, to the free stream value away from the surface means the fluid which is outside before entering, let us take it as a free stream value. Free stream value. Free stream value before entering the boundary is free stream, right? When this fluid is getting inside into the pipe, at the boundaries, the flow resistance is 0. At the boundary, flow resistance is 0. So, we are seeing maximum velocity at the center, right? Maximum velocity is at center. So, whatever the velocity we are sending as an inlet, that velocity will occur at that occurring velocity we are calling as a free stream velocity. This value is equal to some at one point that we are calling as a free stream velocity, right? So this is what your boundary layer, this is what a leading edge, and here what trailing edge. Here what trailing edge. This is what a leading edge. So here at A, B, let us take this point as C. C, it is already there. D, right? So when fluid is getting, this is what here capital U is free stream velocity. Capital U is free stream velocity. So when these free stream velocity fluid is getting in contact with this plate, this is your stationary plate. To the stationary plate, at this point, the velocity is 0. This figure is showing the velocity is 0. As we are moving away from this plate, we are seeing some velocity gradients. That is what du by dy. Velocity gradients. Du by dy. This is all a velocity gradient, right? This is what your boundary layer. It is a boundary layer. So here, this velocity on this plate occurs at that point. We are calling it as a boundary layer thickness. When till where the point where you are inside a velocity is becoming your mainstream velocity. That is what the velocity on the plate small u is equal to 0.99 times of your capital U, right? Till that point, to on the to the plate, the distance between the plate to where your velocity is becoming 0.99 into the stream velocity, till that distance we are calling it as a boundary layer thickness, right? The boundary layer thickness is what the distance between the plate and where your velocity is becoming 0.99 times of your stream velocity, right? Till that, these are all a velocity gradient. We are taking one point, that distance is x, and if you take here, this distance is y. Again, there is a change in a boundary layer thickness. If you take at point B, here you are seeing some boundary layer is less. As you are moving away from the leading edge to trailing edge, again there is a change in a boundary layer thickness, right? These boundary layer thickness are again of three types, right? See here, this is what flow behavior till one point. This we are calling is it as a boundary layer thickness. As you move away, this is your trailing edge, and this is your leading edge, right? Trailing edge and leading edge. So till here, after this we see some variation of the boundary layer, right? After some time again it will become a turbulent boundary layer, right? Turbulent boundary layer. This is what transitional zone, and this is the boundary layer thickness, and this is your turbulent, this transitional, right? This is what laminar. Yes, these are all depending upon the flow, how the flow is getting varied. Here also we are seeing types of boundary layer thickness. This is laminar boundary layer. Till here, this is the transitional zone. After that, the turbulent boundary layer. Right? Again, in that turbulent boundary layer, in the previous session we have discussed. In that again we are seeing laminar sublayer. Laminar sublayer. In this turbulent boundary layer, we are seeing a small, very thin, very negligible one, that is the laminar sublayer, right? This is how your flow, depending upon the flow behavior, the boundary layer thickness is difference, how it is differential, right? So now here, main the boundary layer thickness, it is a distance, as I said it, that is a distance between the plate to where your velocity is becoming your mainstream velocity. This distance, we are calling it as a boundary layer thickness. This is what a boundary layer thickness delta. So the boundary layer thickness distance measured perpendicular to the boundary of the solid body, by which the boundary should be displaced to compensate for the reduction in flow rate on account of boundary layer formation. On account of boundary layer formation, yes. So this is what displacement thickness is. This is what a displacement thickness. Displacement thickness, it is denoted by delta star, right? So this definition is for displacement thickness. Here I am writing displacement thickness. This is what this is for. This is a boundary layer thickness, where the distance between the boundary to the distance where your inlet velocity is becoming 0.99 of your free stream velocity, right? And this is what a displacement thickness. Displacement thickness is what? The distance measured perpendicular to the boundary of the solid body, by which the boundary should be displaced. Boundary should be displaced. The boundary should be displaced to compensate the reduction in a flow rate. To compensate the reduction in a flow rate on account of boundary layer formation. It is denoted by delta star. And one more definition is the distance between perpendicular to the boundary by which free stream is displaced due to the formation of boundary layer. Displaced, free stream is displaced due to the formation of boundary layer. So this is denoted by delta star, right? Delta star. Here the boundary layer thickness, for greater accuracy, boundary layer thickness is this distance plate to here U will become capital U, right? That is what boundary layer thicknesses, right? So here is defined in the terms of mathematical expression to get greater accuracy. We are these boundary layer thickness is classified into three types. One is displacement thickness, second is momentum thickness, third one is energy thickness. These three thicknesses are measured to give the more greater accuracy for the boundary layer thickness, right? The displacement thickness, just now we have discussed, displacement thickness is mainly the distance measured perpendicular to the boundary by which the mainstream is displaced. Mainstream U is displaced on account of the formation of the boundary layer. That is your displacement thickness. It is an additional wall thickness at which you have to add it to compensate for the reduction in a flow rate. The wall thickness that would have to be added to compensate for the reduction of flow rate on account of boundary layer formation, right? So this displacement thickness is denoted by delta star. Now here we are deriving what is a boundary layer displacement thickness is, right? So for this derivation we have taken one stationary plate. Yes, here we are allowing a fluid with free stream velocity, that is capital U, right? So due to this no slip condition, the velocity variation we are seeing, this one is your velocity variation. At the boundary, the velocity is 0. As you are moving upwards, the velocity is varying, right? We are seeing the velocity gradients. Velocity gradient, that is du by dy in y direction. There is change in velocity in as you move in a y direction. As you move in a y direction. So due to this, we are seeing a thin layer, that is a boundary layer, right? So after boundary layer, this is your boundary layer, right? So to this boundary layer thickness varied. So where you choose the boundary layer thickness, till at which point, mean that at this point boundary to the velocity where your small u is becoming 0.99 of your mainstream velocity. That means direct 0.99 means almost nearly approx. It is approx. It is 1. That means small u is equal to capital U, right? So where at this point, till that point, you are considering as a boundary layer thickness, that is delta. Boundary layer thickness, that is a delta, right? So in this layer, we are choosing a small elementary strip of thickness dy. We are choosing on these. This is your elementary strip, and the thickness of these elementary strip is dy. And right from boundary to the elementary strip is your y. The distance from the plate to the elementary strip is y, and the thickness of the elementary strip is dy, right? And this complete is your delta boundary layer thickness. And here the fluid moving with some density, that is rho, and here velocity, which is before entering the fluid velocity, that is capital U, that is free stream velocity, right? So when this fluid getting entered on the plate, we are seeing variations and we are finding a boundary layer thickness, right? Now here we are for calculating a value, we are deriving a displacement thickness, that is delta star. Delta star. So for that, we are assuming we are taking a small elementary strip. The thickness is dy, and where you are taking elementary strip to that point to the stationary plate, that is the y. Before entering the fluid velocities, free stream velocity, that is capital U. So here, assuming unit width, the mass flow rate per second through elementary strip. So this is what your elementary strip. This is elementary strip and the thickness is dy, right? In that elementary strip, the velocity is small u. The elementary strip is small u, right? In this elementary strip, the fluid moving with density rho. So mass flow rate per second is what? Rho. Velocity moving inside the elementary strip, the density is rho, and the velocity is small u into thickness dy. So that we have what here written? Rho u dy. So now I am taking this mass flow per second before entering on the plate. The elementary strip, in elementary strip we got rho u dy, right? So these mass flow per second through the elementary strip, if plate were not there, means what? The small u will not come, because if plate comes, we see the variations in a velocity, right? If there is no plate, then we see whatever the flow velocity the fluid is moving, that capital U, you see a same velocity moving if plate is not present, right? Rho capital U into dy. Rho, density of the fluid into velocity, and that is dy. This is equation 1 and this is the equation 2. Here is the equation 1. On the plate, we have calculated mass flow rate, and again, if plate is not there also, that condition also we have calculated. That is rho capital U into dy. Now, reduction of mass flow rate through the elementary strip. We have reduction of mass flow rate through the elementary strip, that is rho capital U minus small u into dy. This equation 2 minus equation 1. That is rho into capital U minus small u into dy. What is this? This is the velocity of defect. Difference between the capital U minus small u is called a velocity of defect. So here, total reduction of mass flow rate. And here we have seen rho capital U minus small u into dy. When you take a total reduction, for the above equation is for only the small elementary strip, right? That is rho into capital U minus small u into dy. This is for small elementary strip. Now I need total reduction of mass flow rate due to the introduction of plate. So what is that? 0 to this y, 0 to where your capital small u is becoming a capital U. That is nothing but your boundary layer thickness. So the integration of 0 to lambda, 0 to lambda rho into capital U minus small u into dy. This is what a total reduction of mass flow rate when a plate comes in a contact with the fluid. So if the fluid is incompressible, this is the equation. Integration of 0 to delta rho into capital U minus small u into dy is your displacement thickness, right? Let the plate is displaced by delta star. Let the plate is displaced by delta star, that is the displacement thickness. Velocity of flow for the displacement delta x is equal to mainstream velocity. So here, when this mainstream velocity is becoming your mainstream velocity inside on the plate, the fluid velocity is becoming your mainstream velocity, then this complete thickness due to the displacement of place, your delta is becoming delta star, that is displacement thickness. So loss of fluid is flowing through this delta star is equal to rho u delta star. Rho u delta star. So this is what rho u delta star is equal to integration of 0 to lambda rho into u capital U minus small u into dy. When you take a displacement delta star is equal to this rho will get cancelled, and other things, this capital U is taking on the right hand side, and their equation becomes 0 to delta 1 minus small u by capital U into dy. Right? This is how, when you move this delta star, that is equal to integration of 0 to delta capital U by capital U minus small u by capital U, because this is coming to the denominator. So this will become 1. 1 minus small u by capital U. This is how your equation is. For displacement thickness, delta star is equal to integration of 0 to delta 1 minus u by capital U into dy. Right? And now boundary layer thickness. Right? Now we are seeing momentum thickness. Momentum thickness. This is momentum thickness is the distance measured perpendicular to the boundary of the solid body by which a boundary should be displaced to compensate the reduction in movement of the fluid flowing on the account of boundary layer formation. Right? The boundary should be displaced to compensate for the reduction of momentum. For the reduction of momentum of the flowing fluid on account of boundary layer formation. Right? It is also defined as the distance through which the total loss of momentum per second is equal if it were passing a stationary plane. It is denoted by theta. Momentum thickness is denoted by theta. Now we are finding a momentum thickness equation. Theta is what? Right? So again same here, the stationary plate, and before entering the stationary plate, the velocity we call as a free stream velocity, that is capital U. Yeah, this is what your velocity distribution, right? And on this we are taking a small elementary strip. The distance from the plate to the elementary strips is a small y, and the thickness of the plate is dy. And this is what your boundary layer is. Boundary layer thickness delta. Right? So from the figure, again here mass of the flow per second, mass of the flow per second to the elementary strip is rho u into dy. Right? Now momentum, we have to calculate momentum. Momentum is what? Mass flow rate into velocity. Right? Rho u dy into small u is your equation, rho u square into dy. The momentum is rho u square into dy. Now momentum of the same mass of fluid before entering the boundary layer. Before entering the boundary layer means what? Rho small u capital U into dy before boundary layer means that is capital U. So capital U is coming into picture. That is what? Rho small u into capital U into dy. So again this is the equation 2. Here the equation is 1. Right? When you are equating the calculating the loss of momentum, then that is becoming rho u capital U into dy minus rho u square into dy. Right? So this is what a final one is, rho u into capital U minus small u into dy. Rho u. Right? So total loss of momentum is how much? Total loss. Here is a loss on a elementary strip. Now I need a total loss. So here I need total loss. Right? So the total loss is 0 to delta. 0 to delta rho u capital U minus small u into dy. Total loss of momentum is. right? So now let theta, distance by which the plate is displaced, where the plate is displaced when the fluid is flowing with a constant velocity u, right? So here the loss of momentum of fluid flowing, the distance theta with a velocity u is rho theta u square. Rho theta capital U, right? Capital U square. Rho theta capital U square. So we are equating this equation 1 and equation 2. We get rho theta U square is equal to integration of 0 to delta rho U into capital U minus small u into dy. So I'm cancelling this density. Again I'm sending this U square to the right hand side so that I get theta is equal to integration of 0 to delta small u by capital U into 1 minus small u by capital U into dy. This is the momentum thickness. This is what a momentum thickness, and it is useful for in kinetics. Right? This is the momentum thickness. This is the second type of your boundary layer thickness. And now here we are seeing energy thickness. Energy thickness. That is denoted by delta double star or delta E. So this is what energy thickness is. The distance measured. This is also energy thickness is defined as the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced. By which the boundary should be displaced to compensate the reduction in the kinetic energy. To compensate the reduction in kinetic energy of the flowing fluid on account of the boundary layer formation. On account of the boundary layer formation. Right? It is denoted by delta double stars or R delta E. Let this is also same figure, right? This is stationary plate and this is your free stream velocity. Here is the boundary layer and this is your boundary layer thickness. That is distance between a boundary to where your u is becoming a free stream velocity. And here is the velocity distribution and this here is the elementary strip. Elementary thickness of the strip is dy and here the distance from the elementary strip to the boundary is small y, right? And the fluid flowing with density rho, right? From the above figure, the mass flow rate of the elementary strip, as we know, rho u dy. Now here we need kinetic energy of this fluid inside the boundary layer. Inside the boundary layer, kinetic energy. So kinetic energy is what? Half mu square. Yes, half mu square, small u square. That is equal to half mass rho u, mass of flow, rho u dy into small u square. That is small u square. Right? Kinetic energy formula is half mass into velocity square. Right? So mu square. M is rho u dy into small u square. This is on the elementary strip. Elementary strip. And here, kinetic energy before entering the boundary layer. Before entering the boundary layer. What is that? That will become a capital U square. Before entering, the velocity is free stream velocity. Free stream velocity is capital U. Right? So, half rho u dy, that is mass of flow, it, and here the before entering in the velocity is capital, that is capital U square, right? Capital U square. So loss of kinetic energy through the elementary strip is capital U minus small u. So capital U is before entering is half rho u dy into capital U square minus inside the elementary strip is half rho u dy into u square. This is what a kinetic energy loss is. So when you simplify this, you will get half rho u into capital U square. This is common for both, right? So u square minus small u square into dy. Into dy. Half rho u capital U square minus small u square into dy. Right? So total loss is total loss. The thickness. Boundary layer thickness. Boundary to your u is becoming boundary layer thickness from 0 to delta half into rho u into capital U square minus small u square into dy. Here delta E, the distance by which the plate is displaced, the distance by which the plate is displaced to compensate for the reduction in kinetic energy is what? Delta E. Displaced, we have displaced the plate to compensate the reduction of kinetic energy is delta E. So the total loss of kinetic energy is how much? Half rho u delta E into capital U square, right? So this equation 1, this equation and before this equation, both equation when you compare, when you equate, you will get rho is getting cancelled, right? Half of is also. So what you are getting is this u square means delta E u cube u into u square is u cube, that is equal to integration of 0 to delta small u capital U square minus small u square into dy, right? So when you take this capital U cube to the right hand side, you will get half 1 by u cube integration of 0 to delta small u into capital U square minus small u square into dy. Yes, this is taken common 1 by u cube integration of 0 to delta small u into u square minus small u square into dy. Right? So here overall the final expression is delta cube is delta E energy thickness is delta E, that is equal to 0 to integration of 0 to delta small u by capital U into 1 minus u square by capital U square into dy. This is the final expression for energy thickness in boundary layer. So here 3 types of thickness we have discussed here. Boundary layer thickness has 3 to give greater accuracy. We have differentiated the displacement thickness, momentum thickness and energy thickness to compensate the fluid flow which is formed by a boundary layer, right? So first is a displacement thickness. Displacement thickness delta denoted by delta star, and that equation is integration of 0 to delta into 1 minus small u by capital U into dy. This is what a displacement thickness. And second one is energy thickness denoted by delta double stars or delta E. Both way we can denote. Right, so the equation is 0 to delta small u by capital U into 1 minus u square by capital U square into dy. This is the energy thickness equation. Here this is done because to compensate, boundary is displaced to compensate for the reduction of kinetic energy, right, on account of boundary layer formation. This is what a double star is. A displacement thickness, small u is velocity of the fluid at elementary strip, B is the width of the plate, dy is the thickness of the strip and u is your free stream velocity, right? This is momentum thickness. This is distance is measured perpendicular from the boundary of the solid body, by which your boundary should be displaced to compensate for the reduction in a momentum of the fluid flow on account of the boundary layer formation, right? So the delta t theta is equal to integration of 0 to delta small u by capital U into 1 minus small u by capital U into dy. This is the momentum thickness, and this delta double star is sorry, this is theta. This is denoted that theta is momentum thickness. Yes, momentum thickness. Theta. This u is velocity on the strip, b is the width of the plate, and dy is the thickness of the elementary strip, and u capital U is free stream velocity. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.